So Unit 3, Lesson 5 talks about radioactive decay. Here we have 3 different types of decay. They are not the only types of decay, but these are the 3 that we're going to focus on. The first one is alpha decay. Alpha decay is when an unstable atom, or a stable atom for that matter, will give off a positively charged alpha particle. And the notation for the positively charged alpha particle is helium. Okay. With beta decay, what's given off is a negatively charged electron. And then lastly, the other type of decay that you're going to be familiar with is gamma decay, or gamma radiation, which is high energy electromagnetic radiation, which often occurs in the form of something we call photons, which we'll spend some time talking about in the next 2 units or so. So we're going to take a little bit of time to talk about each of these 3 types of decay, which is appropriate because we just closed the spooky season and decay. Now, so the amount of energy that's present in these types of decay can be illustrated through this diagram here. Alpha decay, or alpha particles rather, are relatively large particles in the big picture of particles that are like atomic size. And because it's 2 protons and 2 neutrons, those alpha particles are moving, and they're moving at a rate that is able to be stopped by a single piece of paper. So if there is some type of alpha decay that is occurring, we can stop it with paper. Okay, so it's pretty low energy. Whereas beta decay is a negatively charged electron, and the electron is incredibly tiny compared to the alpha particles. And as a result of that, when it gets going, it being really, really tiny, it has the ability to travel through a piece of paper, but also has the ability to travel through your flesh. And not just like your flesh, like just like going in and stopping, it can make its way all the way through depending on how thick you are or the portion of you that it hits. It will get stopped by metal, sometimes aluminum. So like in the movies, when you see somebody wear an aluminum hat because they want to like protect themselves from the radiation, they're stopping beta decay or something like that. Or so, I don't know. Or when they don't want people to read their minds, that's what they're stopping, is beta decay. And then the neutron comes from nuclear fission reactions, and nuclear fission reactions need that neutron, or release that neutron with lots and lots of energy. So that neutron has more energy, and it will travel through a piece of paper or your hand or the metal or water, or it stops at water. So a lot of times nuclear reactors, when they have their spent product that still might be radioactive, a lot of times they store that in water because the neutron particles, if they happen to get out of the sealed container, will be stopped by the water. And then lastly, the gamma radiation, or gamma decay, is extremely high energy. And because it's not a particle and it's actually energy, it will go through paper and flesh and metal and water and thick concrete and even stop at lead, pretty thick lead. So these are, from low energy to high energy, the different types of radiation or emission that we've kind of covered over the last week or so. Now, an illustration of what occurs is that when uranium-238 undergoes alpha decay to form thorium-234, what happens is that a single alpha particle, that is 2 protons and 2 neutrons, are emitted from the uranium atom. And what's left behind is the uranium atom minus 4 particles, right? 2 protons and 2 neutrons. And what that gives you is a little bit more stable thorium atom, a brand new atom. Now, alpha decay, mathematically speaking, or equation speaking, the rules are still the same. It means that we have to still keep track of the value of the mass number. And since these are both the same formulas, I'm going to kind of just write on the one that's a little bit less crowded. So mass number here is 210. So that means 4 plus 206 is equal to 210. And then 84, which is my atomic number, which is, as you may recall, protons, and the mass number is protons and neutrons. So if I have 84 for my mass number for polonium on the left side, that means that 2 plus 82 has to equal 84 on my right side. Questions about that? In beta decay, this one is a little bit different, and it can be a little bit confusing for some students. So when we have a neutron, right, and here's my best artist rendering of a neutron, what ends up happening is that neutron undergoes some type of a transformation when an electron is given off, and the neutron itself changes into a proton. Now, they're both the same mass. This is 1 AMU. This is 1 AMU. But it just went from being neutral to being to becoming a positive particle, which in this case is the proton. And what's given off is the high-speed electron, like this. And because electrons have almost no mass, they don't really change anything else. So in this instance, again, the math has to be the same. So up on top where my mass number is, my left side is 131, so my right side has to also add up to 131. So 0 plus 131 equals 131. And then my atomic number on the bottom, this is where things get a little hairy. If I have 53 on the left side, -1 plus 54 equals 53. So what happened is that the neutron in the parent atom, in this case the iodine, a neutron changed into a proton, changing the atom itself from iodine into xenon. The beta particle, the electron, was given off, and so both sides have to add up to the same value, which in this case is 53, and students sometimes find that a little tricky. Questions? We'll practice it. Gamma decay occurs when you have an excited atom in its excited state and it gives off energy. So I like to think of the excited atom in its excited state as that kid that was trick-or-treating and ate more candy than they took in. You know what I'm talking about? Like their bag never really got full because they're eating all the candy, and they got really, really excited and hyper and flying around and acting a fool, and eventually they threw up and they kind of wanted to take a nap. You know what I'm talking about? Does anybody know that kid from your little kid, or was that you? Every year I usually get one that admits it was them. Guess not this year. Okay, so what ends up happening is that an atom in an excited state, and this asterisk here is indicating that it is an excited state, it's at high energy, undergoes gamma decay, which means it gives off some type of energy in the form of waves, which I think I should have drawn that a little bit better. Okay. But it doesn't have a mass, and it doesn't have an atomic number, because energy doesn't have the particle, the neutrons and the protons, as we know it. So you end up with a ground state atom of cobalt left over. Questions? So let's practice some. So in this case, what I can see is that I have a helium atom, which tells me it's an alpha particle, which means that the numbers on the right side have to add up to the numbers on the left side. So if I'm looking at my mass numbers, it's going to be, or my atomic number, my mass numbers, it's going to be 205 plus 4 is 209. So that means on the left side, the mass number is going to be 209. The atomic number on the bottom is going to be 82 plus 2, or 84. So I'm going to have 84 for my atomic number for my new element. And when I locate my new element on the periodic table, mine is Jethro, yours might be something else. I locate element number 84, which happens to be polonium, which is PO. Our next one is beta decay. I know it's beta decay because I see the electron present. So that tells me it's beta decay. Now, again, our numbers have to add up on both sides. So in this case, 147 plus 0 has to equal 147. So on the left side, I need a mass number of 147. Now, this is where things get a little weird or wonky, right? 62 plus a negative 1 is 61. Which means that my original atom has to have a mass or an atomic number of 61. And so if I go to the periodic table and I locate element 61, I find out that it is promethium. So now I want you to try the next two. Go ahead and try the next two. Give them the old GHS try. Ready, set, try. So in the case of the third one, the third row, I figured it was beta radiation or beta decay, in large part because I saw the electron that was present. So again, my mass number 255, I needed to have on both sides. So 255 minus 0 is essentially 255. Now with the beta decay, I needed to have my atomic number 99 be the same value on both sides. So I took 99 minus a negative 1, which really means you are adding, so you get 100. So that tells me that the element in question is going to have an atomic number of 100, which according to the periodic table is Fm fermium. The last one, I saw that it was alpha radiation, and it was alpha radiation because of the presence of the helium atom given off. So again, both sides had to add up to the same value. My mass number was 31 on the left side, so 31 minus 4 is 27. And my atomic number, my number of protons is 15 on the left side, so 15 minus 2 is 13, and that gave me the element aluminum. Questions about the type of decay? There is significantly more that goes into decay and things like that. We are just not going to cover it. But in any case, those are your notes for the day.